Hi, I'm Miss Hearn. Let's get started. In this video, we're going to talk about an application in which we use trees, more specifically spanning trees, to keep costs down. But first, let's look at some vocabulary used in this video. Remember, a tree is a connected graph with no cycles. Here we have two versions of tree A. One is a little bit tangled. The edges BF and EI are crossed. On the right, we've untangled those just to emphasize that there really are no cycles, no loops back around. Just like in a tree outdoors in nature, the branches do not reach back around and rejoin with the trunk. What's a spanning tree? Well, a spanning tree is a subgraph that is a tree, and it visits every vertex of the graph, so it spans the whole graph. Tree A is actually a spanning tree of graph B on the left. It's a tree, and it visits each vertex of the graph. It's not the only spanning tree. There can be many different spanning trees. We also need to talk about what a minimum spanning tree is. A spanning tree of a weighted graph that has the lowest weight would be the minimum spanning tree. On the left, I have a weighted graph. Each edge has a dollar value, and you'll notice that on the right, I have highlighted a spanning tree, which consists of the three edges with the lowest dollar amounts. $14, $18, and $22. This would be the spanning tree of lowest weight, or the minimum spanning tree. Now let's look at an application of minimum spanning trees. Consider a telecommunication company that needs to lay down cables to connect several cities. They want to minimize the cost of connecting all the cities while ensuring that each city is reachable from every other city. The cost estimates in thousands of dollars for connecting pairs of cities are given in the table. Our task is to draw a complete weighted graph and find a minimum spanning tree to find the least expensive plan, and then find the estimated cost of that plan. The first step is to draw a complete graph with vertices to represent the cities and edges to represent the connections. Since we can build a connection between any pair of cities, this is a complete graph, and it has vertices A, B, C, D, and E. Next, we're going to use the table to assign weights to the edges. One observation I'd like to make is that in our table, you see symmetry across the diagonal. That's because, for example, to build a connection between city A and city B is the same as building a connection between city B and city A. So I'm going to put the weight of 15 on the edge from A to B. Between A and C, I'm going to put 20. Between A and D, I'm going to put 30. Between A and E, 16. Between B and C, I'm going to put 12. Between B and D, I'm going to put 18. Between B and E, I'm going to put 35. Between C and D, I'm going to put 25. Between C and E, I'm going to put 14. And between D and E, I'm going to put 10. So we have all of our weights assigned on the graph. The next step is to apply an algorithm to find the spanning tree of lowest cost. I'm going to demonstrate Kruskal's algorithm. The first step of Kruskal's algorithm is to choose any edge with minimum weight from all of the edges. So looking at all of the values in the chart or on the graph, we can see that the smallest value is 10. So we're going to choose edge E to D. In step 2, we're going to choose another edge of minimum weight from the remaining edges. The second edge does not have to be connected to the first edge. By the end, we will have connections, but we don't have to have it to start with. The next higher value would be 12. So we're going to choose the edge connecting B and C. Step 3 of Kruskal's algorithm is to choose another edge of minimum weight from the remaining edges, but do not select any edge that creates a cycle. Remember, we're trying to construct a spanning tree, and trees don't have cycles, so you have to keep that in mind when you're selecting edges. So from the remaining values, 14 is the next lowest value on the edge from C to E, so that will be our next selection. Step 4 of Kruskal's algorithm is to repeat step 3 until all the vertices of the original graph are included and you have a spanning tree. So we're going to continue looking for the next lowest value. In this case, out of the remaining values, 15 is the next lowest value. And luckily, if we select 15, which is on the edge from A to B, it does not create a cycle. At this point, we've hit every vertex in our graph. We have A connected to B, connected to C, connected to E, connected to D. So we can use that as our minimum spanning tree. And the value or cost of that tree would be the sum of the weights of all the edges. We have 15 plus 12 plus 14 plus 10, which is going to be 51. So the total estimated cost of this project would be $51,000. You can tell that this would save a lot of money because if we had even selected A to D and E to B, just those two edges alone would have cost $65,000. I hope you found this video helpful. If you did, please give it a thumbs up. That helps other students to find the video. You can also subscribe to my channel, Miss Hearn Mathematics, for more math videos.